On July 27th, a typhoon formed directly on top of the international date line in a stretch of empty Pacific where no storm that would go on to strike China has ever been born. 13 days and more than 6,000 kilometres later, Typhoon Dolphin came ashore in Zhejiang Province, and China raised its highest alert level, not because the wind was extraordinary, but because a storm arriving from that place had no precedent to compare it to. Behind it, 3 named typhoons occupied the same ocean at the same time. One of them was moving in the wrong direction. The storms themselves are not the anomaly. Where the Pacific is now building them is, and the thing doing the building has not finished yet. Quick note before we dive in. If you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs, and drop a comment telling me where you're watching from tonight. Now, let's get into it. Part 1. The line where storms are not born. There is a place in the Pacific Ocean where nothing happens. It sits at roughly 13 degrees north of the equator and 177 degrees east of Greenwich, which is another way of saying it sits almost exactly on top of the international date line. If you dropped a pin there on a globe, you would be pointing at open water in every direction for hundreds of miles. The nearest speck of land worth naming is Wake Island, a coral atoll 2.5 square miles in size with a runway on it, and almost nobody living there. Beyond that, in every direction, there is nothing but warm blue nothing. On July 27th, 2026, at around 2 o'clock in the afternoon Coordinated Universal Time, a tropical cyclone formed in that exact spot. 13.2 degrees north, 176.9 degrees east. The Joint Typhoon Warning Center gave it the designation 12W. The Japan Meteorological Agency counted it as the 13th named typhoon of the year, and the name that went on the bulletins drawn from the rotating list the region's meteorological agencies maintain was Dolphin. 13 days later, that storm came ashore on the coast of mainland China. I want you to sit with that sentence for a second, because it does not sound like much. Typhoons hit China. They hit China every single year, several times a year, sometimes with winds that flatten neighbourhoods and rainfall totals that redraw river systems. A typhoon making landfall in Zhejiang Province in August is roughly as newsworthy as snow in January. Except this one broke a record that nobody had ever thought to check, because until now, nobody had ever needed to. According to China's National Meteorological Center, Typhoon Dolphin is the first typhoon on record to form near the international date line and go on to strike China at tropical storm intensity or above. Not the strongest, not the deadliest, the first. In the entire reliably observed history of tropical cyclones in the northwest Pacific, no storm born that far east has ever completed that journey. Dong Lin, the chief forecaster at the National Meteorological Center, put it in plain language when reporters asked him about it. Dolphin formed near the international date line, he said, something that has never happened since meteorological records began. He listed the storm's defining characteristics like a coroner listing findings. It formed over distant open waters. It had a long lifespan, it had a large circulation system, and it experienced frequent fluctuations in intensity. His conclusion was 3 words long, an exceptionally rare system. So here is the thing I want to establish right at the top because it is the key that unlocks everything else in this video, and because most of the coverage you will see about this storm is going to miss it entirely. The record has almost nothing to do with how hard Dolphin hit. When Dolphin came ashore near the city of Yuhuan in eastern Zhejiang at about 5:30 in the afternoon on Sunday, August 9th, it was carrying maximum sustained winds of 42 meters per second. That is 151 kilometers per hour, which converts to something in the region of 94 miles per hour, which puts it at the equivalent of a Category 1 hurricane. For China, a Category 1 landfall is a Tuesday. It is serious, it is disruptive, it is expensive, and it is entirely within the range of things the country's coastal provinces are built and drilled and staffed to absorb. What made this storm unprecedented was not its arrival, it was its departure point. To understand why that matters, you have to understand something about where typhoons actually come from, because the Northwest Pacific is not a uniform storm factory. It has a floor plan. Tropical cyclones do not form randomly across the basin. They form in a fairly well-defined region determined by sea surface temperature, by low-level convergence of winds, by the depth of the warm water underneath, and by how much wind shear is tearing at the upper atmosphere. Put all of those conditions together and you get a nursery, and that nursery has an address. Under normal conditions, and especially during La Nina years, that address is in the western half of the basin. Observational studies of tropical cyclone genesis put the number at more than 90%. More than 90% of all tropical cyclones in the northwest Pacific form west of 160 degrees east longitude. That is the statistical reality of where storms are born. 9 out of 10 of them, at minimum, get their start in the western half of the ocean, relatively close to the Philippines, close to the Marianas, close to the seas that separate Asia from open water. During an El Nino year, that nursery stretches eastward. The warm water shifts, the convection follows it, and the genesis zone extends out to roughly 170 degrees east. That is a documented, measurable, peer-reviewed shift, and we are going to spend a lot of time on it later in this video because it turns out to be the entire explanation. Dolphin formed at 176.9 degrees east. That is not just outside the normal genesis zone. That is outside the El Nino shifted genesis zone. That is nearly 7 degrees of longitude further east than the far edge of where storms are supposed to be able to get started even in an anomalous year. At that latitude, 7 degrees of longitude is on the order of 750 kilometres. Dolphin was born 750 kilometres past the edge of the map, in a stretch of ocean that the statistics say should not have been able to produce it. And then it did something even stranger. It survived. Here is the problem with being born that far east, if you are a typhoon. You are a very long way from anywhere. From that genesis point to the coast of China is more than 6,000 kilometres of open ocean. Dolphin covered every one of them. 13 days from formation to landfall, more than 6,000 kilometres of track, which is roughly the distance from New York to Rome. Storms do not usually get to do that. A tropical cyclone crossing that much ocean has thousands of extra kilometres in which something can go wrong, and in the Pacific, something almost always does. It can run into a band of wind shear that decapitates its circulation. It can ingest a plume of dry air and choke. It can drift far enough north that the subtropical ridge steering it collapses, at which point the storm recurves out to sea and dies somewhere near the Aleutians without ever threatening a coastline. The overwhelming majority of storms that form in the far eastern reaches of the basin do exactly one of those things. That is why the record book had nothing in it. Dolphin ran the entire length of the ocean instead. It intensified. It reached the top of the scale. It absorbed another named tropical cyclone whole. It struck Japan on the way past. And then it arrived on the Chinese mainland with enough strength left that China raised a red alert, the highest level in its national typhoon warning system, and moved more than 1 million people out of the way. The reasoning behind that red alert is the part I keep coming back to. Chinese authorities did not raise it because the wind speed was extraordinary. They raised it, according to the assessment behind the decision, because a storm arriving from this point of origin, at this strength, had no prior counterpart. They were not warning about a number. They were warning about a category of event that had never been observed before, which meant the usual playbook of comparisons had nothing in it to compare against. That is a genuinely unusual thing for a meteorological agency to admit out loud. Forecasting is built on analogues. You look at what a storm is doing, you find the closest historical match, and you lean on what that match did next. When the analogue file is empty, you are operating without a net, and you make conservative decisions, and you move 1 million people. So the central question of this video is not whether Typhoon Dolphin was strong. Plenty of storms are strong. The question is what put a typhoon on the international dateline in the first place, and what it means that the answer to that question is not finished happening. Because Dolphin was not alone out there. On the same Sunday afternoon that it was tearing across the Zhejiang coastline, the same basin was holding 3 named typhoons at once, with a 4th system under a formation alert days earlier, and a 5th that had already been erased from the map in a way that storms are not supposed to be erased, and one of them was moving in the wrong direction. Part 2. 13 days and 6,000 kilometres. Let me walk you through the journey, because the timeline is where this stops being a statistic and starts being a story. July 27th. Dolphin forms on the dateline as a tropical depression, an unremarkable knot of thunderstorms wrapped around a weak low-pressure centre. At this stage, it is a forecaster's footnote. Systems like this appear in the Pacific constantly, and most of them dissipate within a couple of days. The Joint Typhoon Warning Centre tags it as 12W and begins issuing advisories. The storm is moving west-northwest, pushed along the southern flank of a large area of high pressure that meteorologists call the subtropical ridge. That ridge is worth understanding. because it is the steering wheel for this entire story. Think of it as a vast, slow, clockwise turning mound of sinking air sitting over the middle of the North Pacific. Storms that form on its southern edge get carried west. Storms that drift too far north get caught in its northern flow and flung back east. Where a typhoon sits relative to that ridge determines almost everything about where it ends up, and Dolphin, from the moment it formed, sat exactly in the lane that runs west. By July 29th, it is a typhoon. By the morning of July 30th local time, it is something else entirely. We covered this storm at that stage back in the video from July 30th, when the story was still about a Category 5 sitting harmlessly over open water, with no land in its immediate path. At the time, the striking thing was the intensification curve. Dolphin went from Category 1 equivalent to Category 5 equivalent in something on the order of 24 to 36 hours. The full explosive cycle, according to the analysis published by Yale Climate Connections, lasted less than 36 hours from start to finish. At its peak, it carried maximum sustained winds of 165 miles per hour, or 270 kilometres per hour, with a minimum central pressure of 910 hectopascals. Some tracking analyses circulating afterward argued for a retroactive upgrade to 175 miles per hour at that same 910 hectopascal pressure. That figure was never officially confirmed, so treated as a claim rather than a number, but even the confirmed value puts Dolphin in rare company. It was, at that moment, the planet's 5th Category 5 tropical cyclone of 2026. All 5 had occurred in the Pacific, and that count arriving before the end of July put the year ahead of the pace set in 1997, which remains the all-time record year for Category 5 storms globally with 12. It is worth pausing on the bookkeeping for a moment, because the numbering of these storms tells you something about how busy the ocean was. The Joint Typhoon Warning Center called Dolphin 12W, meaning the 12th tropical cyclone it had assigned a number to in the Western Pacific that season. The Japan Meteorological Agency called it Typhoon number 13. Those two figures disagree because the agencies count slightly different things, but the direction of the disagreement is the interesting part. By the 5th of August, 14 named typhoons had formed in the Northwest Pacific. By the 9th, that count had reached 16. 16 named storms before the second week of August, in a basin whose season nominally runs year-round but whose peak activity is concentrated between July and October. That pace was forecast. Tropical Storm Risk, which issues seasonal outlooks for the world's cyclone basins, published an update on the 7th of July that projected 28 tropical storms, 19 typhoons, and 12 intense typhoons for the Northwest Pacific season. That is approximately 40% above the long-term average. The ocean was expected to be productive this year, and it has been, and Dolphin is the storm that came out of that productivity carrying a record nobody was watching for. Where was it when it peaked? About 181 nautical miles south-southwest of Wake Island. Still out in the empty quarter, still 1,000 miles from anything with a population. NASA's Earth Observing System recorded 140 knots at 6 o'clock in the morning, Coordinated Universal Time on July 30th. Structurally it was textbook. A sharp, warm, symmetric eye. A compact core. The kind of satellite presentation that makes meteorologists go quiet. It completed at least one eye wall replacement cycle, the process in which a storm's inner eye wall collapses and a new, larger one forms outside it, temporarily weakening the system before it reorganizes. Analysts watching it noted the possibility of a third intensity peak attempt afterward. But the intensity is not what makes the track remarkable. The persistence is. Every day that Dolphin held together, it was converting a statistical impossibility into an observed event. The reason no storm from the dateline had ever reached China is not that such a storm is forbidden. It is that the odds compound. Each additional day at sea is another roll of the dice against shear, against dry air, against an unfavourable shift in the ridge. Dolphin rolled those dice for 13 consecutive days and never lost. Which brings me to the number I find genuinely hard to hold in my head. More than 6,000 kilometres. That is the distance the storm covered between its birth on the dateline and its landfall on the Chinese mainland. 6,000 kilometres is further than the distance from Los Angeles to Honolulu and back. It is further than the width of the continental United States plus the Atlantic crossing to Ireland. and Dolphin did it while remaining a coherent, warm-cored, self-sustaining heat engine the entire way. The National Meteorological Centre's characterization of the storm makes more sense in this light. A long lifespan, a large circulation system, frequent fluctuations in intensity. Those three things describe a storm that was constantly being challenged by its environment and constantly recovering. It would weaken, then re-strengthen. It would lose organization, then rebuild it. Over 13 days it did this repeatedly, and the reason it could is the subject of the middle third of this video, and it has to do with what was underneath it rather than what was around it. By early August, the storm's track had begun to bend from west-northwest toward west, and the forecast cone started to include the Ryukyu Islands, and then, further out, the coast of East China. That is the moment this stopped being an oceanographic curiosity and started being an emergency management problem for two countries. There is a detail here that I have to flag, because it is the kind of thing that only looks significant in hindsight. When we looked at this storm on July 30th, the extended forecast guidance already contained a low-confidence suggestion that Dolphin might approach Japan in about a week. At the time, that was the outer edge of what the models were willing to say, the sort of long-range hint that forecasters mention, with heavy caveats, and that usually evaporates within 2 days. It did not evaporate. Dolphin reached Okinawa on August 6th and 7th, almost exactly on the schedule that the least confident line of that forecast had sketched out. A storm that far away, with that many days of ocean left to cross, should not have been that predictable. The fact that it was tells you the steering environment was unusually stable and unusually committed to pushing the system west. On August 6th, with the storm still 1,130 kilometres east of the Zhejiang coast, China's national forecasters were already describing it as exceptionally rare, and provincial governments were already activating emergency responses. Read that again. 1,100 kilometres out, 3 days before landfall. The warnings were already running. On the same day, more than 1,000 fishing boats had already taken shelter at Roshan Fishing Port in Wenling, Zhejiang. The photographs from that harbour are extraordinary. A forest of masts packed hull to hull, an entire regional fishing economy parked and lashed down, waiting. Then, between August 6th and August 9th, Dolphin did the two things that turned this from an unusual storm into the story we're actually here to talk about. It crossed Japan's southern islands, and somewhere out in the open ocean behind it, it swallowed another named typhoon whole. I want to take those in the order the ocean did them, because the second one tells you something about the state of this basin that no single storm's track ever could. Part 3. 36 hours to Category 5. To understand how a storm born in the wrong place stayed alive long enough to cross an ocean, you have to understand what happened to it in the first 72 hours, because that is when Dolphin loaded the tank. Rapid intensification has a formal definition. A tropical cyclone is said to be rapidly intensifying when its maximum sustained winds increase by at least 35 miles per hour, or 30 knots, within 24 hours. It is a threshold that sounds modest and almost never gets crossed. Most storms strengthen gradually, in fits and starts, gaining 10 or 15 miles per hour a day as they slowly organize. Dolphin went from Category 1 equivalent to Category 5 equivalent in roughly 24 to 36 hours. In terms of that formal definition, it did not cross the rapid intensification threshold. It cleared it by a factor of 3 or more. Here is what is physically happening inside a storm when it does that. A tropical cyclone is a heat engine, in the strict thermodynamic sense. It draws energy from the temperature difference between the warm sea surface underneath it and the cold upper troposphere above it, and it converts that difference into rotational kinetic energy. Warm, moist air spirals inward along the ocean surface, absorbing water vapour as it goes. When that air reaches the centre, it turns upward and rises through the eye wall, and as it rises the water vapour condenses into cloud droplets, releasing an enormous quantity of latent heat. That heat warms the core of the storm, which lowers the pressure at the centre, which pulls in more air, which absorbs more water vapour, which releases more heat. It is a feedback loop, and once it gets going cleanly, the only things that stop it are running out of warm water, running into wind shear, or hitting land. Dolphin had none of those problems. It had the opposite of all three. The ocean beneath it was not just warm at the surface. That distinction is going to matter enormously later, so let me plant it now. A storm churns the water underneath it. The wind stress at the surface mixes the upper layers of the ocean, dragging cooler water up from below and spreading it under the storm's own core. That process is called upwelling, and it is the ocean's natural break on tropical cyclone intensity. A storm that sits over a thin layer of warm water floating on top of cold water will effectively strangle itself within a day or two, because it pulls its own fuel supply out from underneath itself. That break did not engage. Dolphin kept accelerating. The reason it did not engage is a number we introduced back in the video from July 27th, and it has only gotten worse since. Ocean heat content, which measures the total thermal energy stored in the upper layers of the sea, rather than just the temperature of the skin at the top, is in its 9th consecutive record year according to the dataset maintained by Chung and colleagues. June of 2026 was the warmest global ocean ever measured, and the Oceanic Nino Index, the standard measure of El Nino strength, stood at plus 0.98 for the April through June season, which places the Pacific firmly in an established and strengthening El Nino state. Those three facts, taken together, describe an ocean in which the warm layer is not a skin, it is a slab, and a storm sitting on a slab of warm water can spin as hard as it likes without ever pulling up anything cold enough to slow it down. The upper atmosphere cooperated as well. Wind shear, meaning the change in wind speed or direction with altitude, is the other great killer of tropical cyclones. A storm needs its column to stand up straight. If the winds at 40,000 feet are blowing significantly faster or in a different direction than the winds near the surface, the storm gets tilted, the warm core gets displaced from the circulation center, and the whole feedback loop falls apart. Out near the date line at the end of July 2026, the shear was low enough that Dolphin's column stayed vertical while it spun itself up. The result was the sharp, warm, symmetric eye that showed up on satellite imagery on July 30th. A compact core, clean outflow at the top, a ring of the most violent weather on the planet organized into a nearly perfect circle a few dozen kilometers across. There is a specific threshold that matters here. The Joint Typhoon Warning Center reserves the term super typhoon for systems with maximum sustained winds of at least 130 knots, which works out to about 150 miles per hour. Dolphin cleared that line and kept going. NASA's Earth Observing System logged 140 knots at 6 in the morning, coordinated universal time on the 30th, and the operational peak came in higher still. It is easy to hear a wind speed and file it away as a number on a scale, so let me put some physics behind it. The force that moving air exerts on a structure does not increase in proportion to wind speed. It increases roughly with the square of the wind speed, and the potential for destruction scales even more steeply than that. A 165 mile per hour wind is not twice as damaging as an 82 mile per hour wind. It is somewhere in the region of 4 times the pressure, and, by the measures engineers actually use for structural failure, close to an order of magnitude more destructive. This is why the top of the intensity scale is not a linear extension of the bottom of it. Every additional increment costs the ocean an enormous amount of energy to produce and delivers a disproportionate amount of damage when it arrives. 270 kilometers per hour of sustained wind, 910 hectopascals of central pressure. That pressure figure deserves a moment of its own, because pressure is the more honest measure of a storm's raw power. Standard atmospheric pressure at sea level is about 1,013 hectopascals. 910 means the column of air above the storm's center weighed roughly 10% less than a normal atmosphere. The ocean surface underneath actually bulges upward in response, and that bulge is one of the ingredients of storm surge. And then, having achieved all of that, Dolphin did the thing that makes it so difficult to forecast. It went through an eye wall replacement cycle. When a storm reaches extreme intensity, the eye wall gets very small and very tight, and the physics of the system begin working against that geometry. A secondary ring of thunderstorms forms outside the original eye wall at a larger radius. That outer ring starts choking off the inflow of moist air to the inner eye wall, which starves and collapses. For a period of hours to a day, the storm weakens noticeably. Then the outer ring contracts and takes over as the new eye wall, and the storm can re-intensify, often ending up broader and larger than it was before, even if its peak wind speed is lower. Dolphin completed at least one of these cycles, and analysts tracking it noted the possibility that it was attempting a third intensity peak afterward. That behavior is exactly what the National Meteorological Center meant by frequent fluctuations in intensity. It also explains the storm's large circulation system, because every eye wall replacement cycle tends to leave a storm physically bigger than it was. Bigger matters. A large circulation is more resistant to disruption than a small one. It carries more angular momentum, it takes longer to spin down, and it draws heat from a wider patch of ocean. Every time Dolphin went through one of these cycles, it traded a little bit of peak wind speed for a lot of durability, and durability was the currency it needed to cross 6,000 kilometres of ocean. Which is why, when the storm reached the Chinese coast 13 days after forming on the date line, it was not a shredded remnant. It was a Category 1 equivalent typhoon with a broad wind field, an enormous moisture load, and enough organisation that a country of 1.4 billion people raised its highest alert level and started moving. But before it got there, it did something to another storm that I have not been able to stop thinking about since I saw the satellite loop. Part 4. The Storm That Ate. Another storm. On August 5th, a second tropical cyclone formed in the western half of the same basin. It was given the name Kujira, the Japanese word for whale, and the Joint Typhoon Warning Center designated it 13W. The Japan Meteorological Agency counted it as typhoon number 14 of the year. In the Philippines, where the National Weather Agency assigns its own local names to any system entering its area of responsibility, it was called Maymay. At noon Coordinated Universal Time on August 5th, Kujira sat near 16.7 degrees north, 122.9 degrees east. That put it roughly 167 nautical miles northeast of Manila, with maximum sustained surface winds estimated at 25 knots, gusting to 35. Modest. A tropical storm at the low end of the scale, the sort of system that does its damage through rainfall rather than wind. At 2 o'clock in the morning on Thursday, August 6th, it made landfall at Magsingal, in Ilocos Sur on the northwestern coast of Luzon, carrying maximum sustained winds of 75 km per hour. The impacts were what you would expect from a wet, disorganized tropical storm crossing a mountainous island. Moderate to intense rain fell across northern and central Luzon. Forecasters flagged 100 to 200 millimeters for La Union, Pangasinan, Benguet, and Zambales, with the usual attendant warnings about flooding in low-lying areas and landslides on saturated slopes. By Thursday afternoon, Kujira had finished crossing northern Luzon and emerged over the Philippine Sea on the other side, weakened first to a tropical depression and then to a low-pressure area. Even in that weakened state, Kujira was not the only thing making the Philippines wet that week. Dolphin, still hundreds of kilometers out to sea and never coming anywhere near the archipelago, was pulling on the southwest monsoon flow hard enough to drench Luzon on its own. That is what a large circulation does. A typhoon that size does not need to hit you to soak you. It reaches out across an entire sea and drags the monsoon over your head, and the rain that falls has the storm's fingerprints on it, even though the storm itself is 1,000 kilometers away. Two systems, one of them present and weak and one of them absent and enormous, were putting water on the same islands at the same time. Under normal circumstances, that is the end of the story. A tropical storm crosses a landmass, its circulation gets torn apart by terrain, and it fades into an area of disorganized showers that eventually dissolves. Luzon in particular is very good at killing tropical storms. The island's spine is mountainous, the Cordillera Central rises to well over 2,000 meters, and a weak system dragging its circulation across that terrain loses its low-level inflow and its symmetry within hours. Kujira did lose both. What it did not lose was the will to come back. The remnants reorganized enough that the Joint Typhoon Warning Center issued a second tropical cyclone formation alert on the system, this time near 23 degrees north, 141 degrees east, judging that it was likely to strengthen back into a tropical depression within 24 hours. Look at where that is. 23 north, 141 east, puts the remnants out past the Bonin Islands, roughly 18 degrees of longitude east of where the storm had made landfall in Ilocos Sur 2 days earlier. That is not a system limping westward toward Asia. That is a system that got picked up, carried back out into the open Pacific, and handed a second chance in warmer, deeper water than the shelf it had died over. For about a day, the Northwest Pacific was tracking a resurrected storm, and then it disappeared. Not weakened, not dissipated in the ordinary sense. Kujira dissipated after being absorbed by Typhoon Dolphin. I want to be careful about what that means, because it is a genuinely different phenomenon from a storm simply dying. When two tropical cyclones come within a few hundred kilometers of each other, they begin to interact. The classic version of this is called the Fujiwara effect, named for the Japanese meteorologist who described it a century ago, in which two systems of comparable strength begin orbiting a common center like a pair of dancers. It is one of the more visually striking things you can see on a satellite loop. Sakuhei Fujiwara described the behavior in the early 1920s, working not with satellites, which did not exist, but with laboratory experiments on vortices in fluid. He was studying how two spinning columns in a rotating fluid influence each other, and he found that they orbit a point between them, drawing gradually closer as they turn. A century later, that laboratory result is one of the standard tools forecasters use when two tropical cyclones show up on the same satellite image, because water and air obey the same equations. But that symmetrical dance only happens when the two storms are roughly evenly matched. When one is dramatically stronger than the other, the interaction is not a dance. It is an absorption. The stronger storm's circulation is vast, and the outer bands of that circulation sweep across the weaker system. The larger storm's inflow starts pulling on the smaller storm's moisture, drawing the warm, saturated air that the smaller system needs to survive into its own eyewall instead. The weaker system's vorticity, meaning the rotational energy stored in its spin, gets stretched and sheared and eventually merged into the larger circulation. The wind field of the smaller storm stops being an independent thing and becomes a feature of the bigger one. And then, on the satellite imagery, it is simply not there anymore. It has been consumed. That is what happened to Kujira. A named typhoon, tracked by 3 separate national meteorological agencies, given a designation number and a local Philippine name and its own set of warning bulletins, was eaten by another storm. And this is where I want to bring the thread back to the central question, because storm absorption is not just a curiosity, it is a symptom of density, and Kujira was not even the only other thing in the water. The Pacific Disaster Center's bulletins from that stretch of early August were tracking 3 items in a single update: Tropical Cyclone 12W, meaning dolphin, Tropical Cyclone 13W, meaning Kujira, and an area of disturbed weather designated Invest 96W. An invest is not a storm. It is a candidate, a region of convection that forecasters have flagged as worth watching and assigned computing resources to. Having one on the board alongside 2 named systems is normal. It is what comes next in this story that is not. For one tropical cyclone to consume another, the 2 of them have to be close enough to interact, and that requires a basin producing multiple systems in overlapping regions at overlapping times. If you have 1 storm at a time, absorption cannot happen. If you have 5, it becomes not just possible but likely. The reason Dolphin was in a position to eat Kujira is that the Northwest Pacific in the first week of August 2026 was crowded, and it was crowded because the conditions that produced Dolphin's anomalous berth on the dateline were producing storms everywhere else in the basin at the same time. There is a second consequence, and it is the one that connects directly back to Dolphin's improbable survival. When a large typhoon absorbs a smaller system, it does not just remove a competitor, it inherits the fuel. All of that warm, moist tropical air that Kujira had spent days gathering over the Philippine Sea got folded into Dolphin's circulation. The moisture load that eventually fell on Zhejiang as 250 to 500 millimeters of rain was not sourced entirely from the water Dolphin passed over. Some meaningful fraction of it was Kujira's. The storm that broke the record for the longest improbable journey in the basin's history was, in its final days, running partly on another storm's fuel. Which raises a question the record book cannot answer, and one I keep turning over. If a crowded basin lets big storms eat small ones and grow larger in the process, what happens to the size of the biggest storms in a season where the basin is producing 16 named systems before the second week of August? Dolphin was about to demonstrate part of the answer over a chain of Japanese islands with 1.5 million people living on them. Part 5. The first real numbers. 6 people were injured. That is the human toll from Typhoon Dolphin's passage through Japan's southern islands on August 6th and 7th, and I want to start with it because it is the first point in this entire 13-day journey where the storm actually touched anybody. For 10 days, Dolphin had been an object of purely scientific interest, spinning over water with nobody underneath it. Okinawa is where it stopped being an abstraction. 5 of the 6 were elderly residents in Okinawa Prefecture, all with injuries described as non-life-threatening. The 6th was a person injured in Kagoshima Prefecture, further north along the island chain. That is the whole casualty list from a system that had been a Category 5 equivalent super typhoon a week earlier. To give that number some scale, Okinawa Prefecture is home to roughly 1.5 million people, spread across a chain of islands that stretches for hundreds of kilometres southwest from the Japanese main islands toward Taiwan. Kagoshima Prefecture, at the northern end of the same chain, holds more than 1.5 million more. A system with Dolphin's windfield passing over that much inhabited coastline and producing 6 injuries is not a near miss. It is a direct hit that landed on a population that was ready for it. The wind numbers explain some of that. By the time Dolphin reached the Ryukyus, it was carrying maximum sustained winds of 162 km per hour, which is about 101 miles per hour, with gusts reaching 216 km per hour, or 134 miles per hour. Those are serious numbers. They're also a very long way down from 270 km per hour, which is what the storm had been doing over open water south of Wake Island on July 30th. The electrical grid took the brunt of it. Nearly 39,000 buildings in Kagoshima lost power, along with more than 12,000 in Okinawa. Some reporting put the combined figure above 50,000 buildings without electricity. Both of Japan's major domestic airlines, All Nippon Airways and Japan Airlines, cancelled flights into and out of Okinawa. Now, 6 injuries from a 100-mile-per-hour typhoon crossing a populated island chain is a remarkably good outcome, and it is not luck. Okinawa is one of the most typhoon-exposed inhabited places on Earth. The prefecture sits directly in the path of the Northwest Pacific's main storm highway, and it has been absorbing direct hits for as long as there have been people living there. The built environment reflects that. Okinawan construction leans heavily on reinforced concrete, rather than the timber framing common on Japan's main islands. Roofs are low and heavy, windows have shutters, utilities are hardened. Schools and public buildings double as shelters, and the population knows the drill without being told. This is what a well-adapted society looks like when a serious storm arrives, and it is worth naming because the rest of this video is about a storm doing something no storm has done before, and it would be easy to come away from that with the impression that nothing works. Things work. Okinawa is proof. The power outages are the exception that proves the rule, and they are worth following through to the end of the chain rather than leaving as a statistic. 50,000 buildings without electricity in southern Japan in early August is not an inconvenience measured in dark rooms. It is 50,000 buildings without air conditioning during the hottest and most humid part of the Okinawan year, in a prefecture with an elderly population and a climate that regularly pushes the heat index into genuinely dangerous territory. It is refrigeration failing in homes and small businesses. It is water pumps in taller buildings going quiet. It is the medical devices that people keep at home running on battery reserve. The 5 elderly residents who were injured are the visible casualties. The public health burden of a multi-day outage in that heat is real, and it does not show up in an injury count. Then there is the reason storms usually weaken over that island chain, and the reason this one did not weaken enough. Island interaction is a genuine break on tropical cyclones. A storm crossing a mountainous island loses the smooth ocean surface that its low-level inflow depends on, and the friction and terrain begin to disrupt the circulation. Even the shallower, more mixed shelf water around an island chain can be enough to cut into the heat supply. The Ryukyus, though, are narrow. Dolphin was not crossing a landmass so much as threading between islands, and the water on the other side in the East China Sea was warm and shallow and had been baking all summer. Whatever the islands took out of the storm, the sea beyond them put back in. But I want to pull the thread back to the anomaly, because Okinawa also gives us the first hard evidence of something important about Dolphin specifically. Consider what the storm had already done by the time it got there. It had formed on the international date line. It had crossed several thousand kilometres of ocean. It had peaked at Category 5 and come back down. It had gone through at least one eye-wall replacement cycle. And after all of that, it arrived at the Ryukyu Islands still carrying gusts of 134 miles per hour and enough rain to matter. There is a useful way to think about what a typhoon's lifetime actually costs it. Every hour a storm spends spinning, it is doing work against friction at the sea surface, and that work has to be paid for continuously out of the heat it extracts from the water. A tropical cyclone is not a flywheel coasting on stored momentum. It is an engine that stops the moment the fuel line is cut, which is why storms die within a day or two of moving over land or cold water. 13 days of continuous operation means 13 days of uninterrupted fuel supply every hour without a single meaningful gap. A storm that has travelled that far is supposed to be running on fumes. Distance is supposed to be the great equalizer. Every kilometre of ocean a typhoon crosses is a kilometre over which it can encounter something that kills it, and the statistical expectation for a system that old and that far travelled is a weakening, disorganised mess. Dolphin was still a functioning, dangerous typhoon after 10 days at sea, and then it kept going for 3 more. That persistence is the actual story, and it is the thing that made the Chinese record possible. Without it, Dolphin ends its life as a tropical storm somewhere in the East China Sea, and nobody writes anything down. There is one more detail from the Japanese leg worth flagging, because it will matter when we talk about what is coming next. Dolphin's passage across the southern islands did not weaken it enough to matter. It emerged into the East China Sea and continued west, with its circulation intact and its moisture load largely undiminished. Some of that resilience came from the water underneath it, and some of it by then came from Kujira. The airline cancellations tell the same story from a different angle. When All Nippon Airways and Japan Airlines both suspend service to and from Okinawa, they are not reacting to what the weather is doing at the airport that hour. They are making a commercial decision 2 or 3 days in advance based on a forecast, accepting a known cost to avoid an unknown one, and stranding thousands of passengers in the process. Airlines do that when the forecast is confident. It is another small piece of evidence that by the first week of August, nobody in the region was treating Dolphin as a maybe. 3 days after Okinawa, a country of 1.4 billion people was going to find out what was left. Part 6. 4 Days of Warnings. On August 5th, 4 days before landfall, more than 1,000 fishing boats crowded into Roshan fishing port in Wenling, Zhejiang Province. The photographs are worth looking up because they communicate something that no advisory bulletin can. A forest of masts packed hull against hull, an entire regional fishing fleet lashed down and parked. The working economy of a stretch of coastline simply switched off and tied to a dock. That is a decision that costs money. Every boat in that harbour is a boat not fishing, and the fleet went in 4 days early. China's typhoon response system runs on 4 levels, numbered in reverse of what English speakers usually expect. Level 4 is the lowest tier of activation, and Level 1 is the highest, and the system is designed to escalate as confidence in a forecast increases. What is notable about the Dolphin sequence is how early the ladder started climbing. At 2 o'clock on the afternoon of August 6th, Zhejiang Province adjusted its maritime typhoon emergency response to Level 4. Fujian Province, immediately to the south, activated a Level 4 typhoon emergency response the same afternoon. And at the national level, China's National Flood Control and Drought Relief Headquarters and the Ministry of Emergency Management jointly activated a Level 4 emergency response covering both provinces. At 3 o'clock, 21 water passenger transport routes in Zhoushan, Zhejiang were suspended. Zhoushan is an archipelago of more than 1,000 islands off the Zhejiang coast, and those ferry routes are not tourist conveniences. They are how people get to and from home, how supplies reach island communities, and how the workforce of one of the world's great cargo port complexes moves around. Suspending 21 of them at once is the maritime equivalent of closing a metro system. There is also a chronology to how the confidence built, and it is instructive. Days before any of that, when Dolphin was still far out in the Pacific, Chinese forecasters were publicly saying that the storm's track and impact would not become clear until August 6th. That is unusual candour from an operational agency, and it reflects exactly the problem Donglin described. A system that formed over distant open waters, with a long lifespan and frequent intensity fluctuations, is a system whose forecast cone stays wide for longer than normal. Provincial authorities in Shanghai, Zhejiang and Fujian did not wait for the cone to narrow. They began activating while the uncertainty was still large. At 5 o'clock that afternoon, Dolphin was still 1,130 kilometres east of the Zhejiang coast. I want to sit on that number because it is the one that separates this response from an ordinary one. 1,100 kilometres is the distance from London to Rome. The storm was that far out to sea, 3 full days from landfall, and provinces were already activating emergency machinery. At 6 o'clock, Ningbo temporarily shut down all coastal attractions and high-risk marine tourism activities. On the same evening, the Guangdong Maritime Safety Administration, several hundred kilometres to the southwest and well outside the forecast landfall zone, imposed traffic controls on vessels travelling northward through the southern entrance of the Taiwan Straits. That is a province that was never going to take a direct hit, closing a shipping lane on the strength of a forecast. The National Marine Environmental Forecasting Centre maintained an orange alert for waves in Zhejiang's coastal waters, warning of large to very large seas. Wave alerts are the quiet ones, and they deserve more attention than they get. A typhoon does not need to reach you for its waves to. Swell generated under a storm's core propagates outward faster than the storm itself moves, which means the sea state at a coastline deteriorates well before the wind does. Long-period swell arriving from a distant typhoon is the mechanism behind most of the drownings that get recorded in the days before a landfall, because the sun is out, the wind is light, and the ocean looks inviting right up until a set arrives that is twice the size of anything that came before it. Zhejiang's orange wave alert was in force while the storm was still 1,100 kilometres away. There is a cost to all of this, and it is not small. Every suspended ferry route, every closed attraction, every boat tied to a dock, and every shipping lane under traffic control is economic activity that does not happen. Chinese coastal provinces run some of the densest industrial and logistics networks on the planet, and switching them off for several days is measured in serious money. Emergency managers everywhere face the same asymmetry. The cost of over-preparing is visible, immediate, and lands on identifiable people, while the cost of under-preparing is hypothetical right up until it is a body count. Why so early and why so wide? Because of the thing we established at the beginning of this video. The forecasters had no analogue. Every operational forecast leans on precedent. A meteorologist looks at a storm's structure, its environment, and its track, and then reaches for the closest historical match to answer the question of what happens next. That is not a shortcut. It is the accumulated pattern recognition of decades of observation, and it is genuinely good at what it does. But it only works when the file drawer has something in it. Dolphin's file drawer was empty. A typhoon born on the international date line that maintained itself across 6,000 kilometres of ocean and arrived on the Chinese coast at typhoon strength was, according to China's own National Meteorological Centre, something that had never been recorded before. There was no previous storm to point at and say, this one behaved like that one, so expect this. It is worth being concrete about how much of modern forecasting rests on that drawer. When a hurricane specialist looks at a storm approaching a coastline, the numerical models give them a spread of possible tracks and intensities, and the models disagree with each other, sometimes wildly. Resolving that disagreement into a single official forecast is a judgment call, and the judgment is informed by what similar storms in similar environments have historically done. Did systems with this structure, at this latitude, with this steering pattern, tend to overperform the models or underperform them? That accumulated intuition is why human forecasters still consistently beat raw model output. When you cannot forecast by analogy, you forecast by caution. You assume the storm can do more than you expect, because you have already been surprised once by the fact that it exists at all. You activate early, you activate wide, and you accept the economic cost of a response that might turn out to be larger than the event required. Donglin's assessment at the National Meteorological Centre laid out exactly which properties made the storm hard to pin down. It formed over distant open waters, it had a long lifespan, it had a large circulation system, and it experienced frequent fluctuations in intensity. Every one of those four characteristics is a forecasting problem. Distant formation means less observational data early on. Long lifespan means more accumulated track error. Large circulation means impacts spread far from the centre, and frequent intensity fluctuations mean that whatever category the storm is in today is a poor guide to what category it will be in tomorrow. There is one more thing this sequence demonstrates, and it is the reason I wanted to walk through it hour by hour rather than summarising it. Every single action on that list, the fishing fleet, the ferry suspensions, the emergency response activations, the shipping controls, happened before the storm was close enough for anybody on the coast to see it. The sky over Wenling on the 5th of August was, as far as anyone standing under it could tell, an ordinary summer sky. The entire response was executed against a forecast, on the strength of numbers on a screen, days ahead of any physical evidence that anything was coming. That is worth appreciating for its own sake. The gap between a satellite measurement of a spiral of cloud 1,000 kilometres out to sea and a fishing captain deciding to tie up his boat is an enormous chain of institutions, instruments, models and trust, and every link in it held. By the morning of August 9th, the caution had escalated all the way to the top of the scale, and China issued a red alert. That decision, and the specific reasoning behind it is where this story stops being about meteorology and starts being about what a country does when the record book runs out. Part 7, 5:30. In the afternoon. How do you warn a population about a storm when your justification is not a number but an absence? At about 5:30 in the afternoon, local time, on Sunday, August 9th, 2026, Typhoon Dolphin made landfall near Yuhuan in eastern Zhejiang Province. Yuhuan is a coastal city administered by the larger municipality of Taizhou, which is why some accounts of that afternoon describe the landfall as occurring at Taizhou and others at Yuhuan. They are describing the same event. The storm came ashore with maximum sustained winds of 42 meters per second near its center. That is 151 kilometers per hour, equivalent to a Category 1 hurricane on the Saffir-Simpson scale. Roughly an hour later, at about 20 minutes to 7 in the evening, Dolphin made a second landfall further down the coast at Wenzhou, Zhejiang. It was the most powerful tropical cyclone to strike China in 2026. Two landfalls in the space of about an hour sounds strange if you picture a coastline as a straight line, but the Zhejiang coast is not a line. It is a shredded edge of bays, peninsulas, river mouths, and thousands of offshore islands. A storm center that comes ashore over a peninsula can slide back over water on the far side of it, and then come ashore again on the next stretch of land. And the meteorological agencies record both crossings because both crossings matter to the people underneath them. The eye that crossed Yuhuan and the eye that crossed the Wenzhou coast an hour later were the same eye. What the two entries in the record really describe is a storm center, grinding southwest along a coastline rather than punching straight through it. 42 meters per second is a figure worth unpacking as well, because meters per second is the unit that Chinese and Japanese agencies use, and it does not land intuitively for most people. 42 meters per second means that in the time it takes you to say the number out loud, the air at the storm's core has travelled the length of a football field. Sustained, not a gust, for hours. Earlier that same day, China had issued a red alert. In the Chinese warning system, red is the top of the scale, the level reserved for the most severe and imminent threats, and it triggers the fullest possible mobilization of emergency resources. Here is the part I find genuinely remarkable. The red alert issued on Sunday was based on a judgment that a storm from this point of origin, at this strength, has no prior counterpart. Read that reasoning carefully, because it is not the reasoning agencies normally give. Warnings are usually justified by magnitude. This storm has winds of X, a surge of Y, and rainfall of Z. Therefore the alert level is red. The justification here was categorical rather than quantitative. The alert was raised because this kind of storm had never been observed before, and therefore the ordinary basis for predicting its behavior did not exist. The response matched the reasoning. More than 1 million people were evacuated ahead of landfall. Separate reporting on the coastal provinces described nearly 100,000 residents relocated from specific high-risk areas, which appears to be a subset of the broader total. More than 1,000 flights were cancelled. Railway services along the coast were suspended. Those two evacuation figures, the million and the 100,000, are worth separating rather than treating as a contradiction. The larger number is the total population moved out of harm's way across the affected provinces, which in Chinese practice includes people relocated from unsafe housing, low-lying districts, construction sites, and areas with landslide exposure. The smaller number describes relocations from specific coastal high-risk zones. They are nested, not competing. What both of them describe is a logistics operation that has to identify, notify, transport and shelter a population the size of a major city in under 72 hours on the strength of a forecast. More than 1,000 cancelled flights is its own kind of number. That is not one airport standing down. That is a regional aviation network unwinding itself, with the knock-on delays propagating across the country and beyond for days afterward. The rainfall forecast was the part that worried planners most. 250 to 500 millimeters was forecast for parts of central and eastern Zhejiang. At the upper end of that range, half a meter of water, falling on terrain that runs from coastal plain up into hills within a few dozen kilometers, is a landslide and flash flood scenario rather than a wind scenario. And the rain footprint was enormous, which is what you get from a storm with a large circulation. Torrential rain was forecast through August 10th across Zhejiang, Shanghai, northern Fujian, northeastern Jiangxi, central and southern Anhui, and much of Jiangsu. In Shanghai, residents were photographed on the afternoon of August 9th, walking through the streets in raincoats, leaning into wind, umbrellas turned inside out, more than 200 kilometres from where the eye came ashore. The forecast then extended the misery inland and northward. Heavy to torrential rain was expected across parts of central and eastern China from Saturday the 8th through Wednesday the 12th, followed by further downpours in North China, Inner Mongolia, and southern northeast China from Wednesday through Friday, as dolphins' remnants interacted with cold air. After landfall, the storm was forecast to track westward, then slow over central and southwestern China while gradually losing strength. That last sequence is the one that historically produces the worst outcomes, and the mechanism is worth walking through step by step, because it is the least intuitive part of typhoon risk. A tropical cyclone that comes ashore immediately begins to die. It has lost its heat source, and its wind field starts to decay within hours. But the moisture does not go anywhere. A large typhoon carries an enormous column of tropical water vapour inland with it, and as the wind decays, the storm slows down, which means that column of moisture now sits over the same real estate for longer. That alone can produce catastrophic rainfall totals. Then add cold air. When the decaying remnants drift far enough north to meet a front pushing down from the continental interior, the cold air wedges underneath the warm tropical air and forces it upward. Lifting saturated air is the single most efficient rain-producing process in the atmosphere. The storm's own circulation is no longer doing the work. The frontal boundary is doing it, and it can do it for days. That is how a typhoon that made landfall in Zhejiang ends up flooding Inner Mongolia. The wind story ends at the coast. The water story runs inland for a week, and it arrives in places that never saw a warning cone, days after the news coverage has moved on. But now I want to come back to the thing I flagged at the very beginning of this video, because we have finally arrived at the point where it can be stated properly. Everything you just heard about the landfall is, by Chinese standards, ordinary. A Category 1 equivalent strike on Zhejiang in August is a normal event in a normal season. The evacuation numbers are large because Chinese coastal population density is large, and Chinese emergency management is aggressive, not because the storm was exceptional at the moment it arrived. Strip away the record and what you have is a competent country handling a routine typhoon competently. The record is not in any of those numbers. The record is in a coordinate. Imagine two typhoons hitting Zhejiang on the same afternoon with identical wind speeds, identical pressure, identical rainfall. One of them formed in the Philippine Sea 5 days earlier, at around 130 degrees east, which is where these storms normally come from. The other formed on the international date line 13 days earlier. Standing on the seawall at Yuhuan, you could not tell them apart. On paper, they are the same event. They are not the same event. The first one is the ocean doing what the ocean does. The second one is the ocean doing something it has not been observed doing, which means whatever produced it is either new or rare enough that we have not caught it before, and either of those answers should make you want to know more. Dolphin's significance is that it started at 13.2 degrees north, 176.9 degrees east, 13 days and more than 6,000 kilometres before it reached Yuhuan. Everything else in this story, the evacuations, the red alert, the rainfall, the fishing fleet in Wenling Harbour, is downstream of that one fact. This was not a strong storm that came from somewhere ordinary. It was an ordinary storm at the end that came from somewhere impossible, which leaves exactly one question worth asking, and it is the question the rest of this video exists to answer. What put it there? Part 8. The nursery moved. The answer is that the Pacific Ocean has moved its furniture, not metaphorically. There is a physical object in the Pacific, thousands of kilometres across, that determines where tropical cyclones can be born, and over the past several months it has been sliding east. Dolphin was not an exception to the rules of where typhoons form. Dolphin formed exactly where the rules said it should, once you account for the fact that the rules had relocated. The object in question is the warm pool. In the western equatorial Pacific, stretching from the seas around Indonesia and the Philippines out into the open ocean, sits the largest expanse of warm surface water on the planet. Sea surface temperatures there routinely sit above 28 degrees Celsius, across an area larger than the continental United States, and that warmth is not a thin veneer. It extends down through a deep layer of the upper ocean. This is the engine room for a substantial fraction of the world's weather, and it is the reason the Northwest Pacific produces more tropical cyclones than any other basin on Earth. Under ordinary conditions, the warm pool sits in the west. That is where the trade winds put it. The prevailing easterly trade winds blow steadily across the tropical Pacific, dragging surface water westward with them, and over the width of an ocean that dragging piles warm water up on the western side. The sea surface in the western Pacific is measurably higher than it is in the east, for exactly this reason. Warm water accumulates where the wind pushes it. The scale of that piling is easy to underestimate. Because the trade winds have been pushing water west across the entire width of the Pacific for as long as there have been trade winds, the sea surface in the far western Pacific sits appreciably higher than it does off the coast of South America. 0.5 metre of difference in sea level, maintained by nothing but wind, across 10,000 kilometres of open ocean. The Pacific is permanently tilted, and the tilt is held up by air. Sitting on top of that tilt is an atmospheric loop that meteorologists call the Walker circulation. Air rises over the warm western Pacific, where all that heat is driving convection, flows east at high altitude, sinks over the cool eastern Pacific, and returns west along the surface as the trade winds. It is a conveyor belt, and it is self-reinforcing. The warm water drives the rising air drives the trade winds, and the trade winds pile up the warm water. Each part of the loop props up the other two. That accumulated warmth is what feeds cyclone genesis, and that is why the statistics come out the way they do. Under La Nina conditions, when the trade winds are strong and the piling is at its most extreme, more than 90% of all tropical cyclones in the northwest Pacific form west of 160 degrees east. The nursery is packed into the western half of the basin because the fuel is packed into the western half of the basin. El Niño inverts that arrangement. During an El Niño event, the trade winds weaken, and in strong events they can reverse outright over stretches of the equatorial Pacific. The mechanism that had been piling warm water in the west relaxes, and the warm water sloshes back east. Sea surface temperatures rise across the central and eastern equatorial Pacific. And because atmospheric convection, meaning the towering thunderstorm activity that drives the whole system, follows the warmest water, the region of rising air and low-level wind convergence shifts east with it. Tropical cyclones need that convergence. They form where air is being pulled together at low levels and lifted, because that is where an initial rotating disturbance can organize into a closed circulation. When the convergence moves, genesis moves. The measured result is unambiguous. During El Niño conditions, tropical cyclone genesis locations in the northwest Pacific extend eastward to approximately 170 degrees east. That is roughly 10 degrees of longitude further east than the La Nina distribution, and at tropical latitudes 10 degrees of longitude is on the order of 1,100 kilometres. The entire storm nursery slides 1,000 kilometres toward the date line. Because the Walker circulation is a loop, weakening any one part of it weakens all of it. Warm water sloshing east means convection moving east, which means the rising branch of the loop moves east, which means the trade winds that were doing the piling weaken further, which lets more warm water slosh east. Once an El Niño gets going, it tends to reinforce itself, which is why these events develop over months rather than days, and why they are so difficult to stop once they start. That finding is not new, and it is not controversial. It has been documented across multiple studies of tropical cyclone activity in the western North Pacific, including work published in the Journal of Climate, examining how different flavors of El Niño affect where and how storms form. That distinction between flavors matters more than it sounds. Not all El Niño events warm the same stretch of ocean. Some concentrate their warming in the far eastern Pacific off South America, and some concentrate it in the central Pacific near the date line. And the research finds that where the warming sits determines how much the genesis zone shifts and how the resulting storms behave. An event centered further west pushes the nursery differently than an event centered further east. The location and the intensity of the warming are separate variables, and both of them matter. The eastward and equatorward shift of genesis under El Niño is one of the more robust results in the field, and the physical reasoning behind it is straightforward enough to explain in a paragraph, which is not something you can say about most climate teleconnections. Now hold that number against the one we started with. The El Niño shifted genesis zone reaches to about 170 degrees east. Typhoon Dolphin formed at 176.9 degrees east. The storm was born nearly 750 kilometres beyond the far edge of the anomalously shifted nursery. Not beyond the normal zone, beyond the shifted one. This is a storm that formed past the eastern boundary of where storms form in the years when storms form furthest east. And that single coordinate is the load-bearing fact of this entire video, because it converts the story from an anecdote into a measurement. A record-breaking storm is interesting. A record-breaking storm that lands precisely at the far end of a documented, physically explained ongoing shift is something else. It is a data point telling you how far the shift has gone. The consequence chain that follows from that shift is where it gets genuinely important, and recent research has traced it explicitly. When Genesis moves east, storms are born further from land. A storm born further from land spends longer over open water before it encounters anything that can stop it. A storm that spends longer over open water has more time to intensify, and therefore tends to reach a higher peak intensity. And a storm that forms that far east and still tracks westward produces a longer track, which means it can reach landfall locations that storms from the ordinary nursery would never reach. Read that chain again with Dolphin in mind, because it describes the storm's life history point by point. Born at the far eastern edge, 13 days at sea, Category 5 peak, more than 6,000 kilometres of track, landfall on the Chinese mainland. Dolphin is not an anomaly that defies the science. Dolphin is the science, expressed as completely as it has ever been expressed, in a single storm. There is a second half to the shift that gets less attention and is worth naming. Genesis under El Nino moves east, and it also moves equatorward, closer to the equator itself. That combination has a particular consequence for track length. A storm forming closer to the equator has weaker Coriolis forcing acting on it initially, which tends to delay the poleward drift that eventually pulls a typhoon out of the tropics and into the mid-latitude westerlies. It stays in the deep tropics longer, riding the easterly flow west, which is exactly the recipe for the long, straight, ocean-spanning track that Dolphin drew across the Pacific. The same El Nino also has an opposite effect on the other side of the world, and it is a useful contrast. By altering the atmospheric circulation across the tropics, El Nino events typically increase vertical wind shear over the tropical Atlantic, which suppresses hurricane formation there. The same ocean state that is loading the Pacific tends to quiet the Atlantic. One basin gets busier while the other goes still, which is why global tropical cyclone counts are far more stable from year to year than any individual basins. The El Nino driving that shift is well established and officially recognized. On the 11th of June 2026, NOAA's Climate Prediction Center upgraded its ENSO alert status from El Nino Watch to El Nino Advisory, meaning El Nino conditions were no longer anticipated but observed in the tropical Pacific. The probability of those conditions persisting through the Northern Hemisphere winter was placed at greater than 96%, and the Oceanic Nino Index, which we looked at in the video from July 27th, stood at plus 0.98 for the April through June season, comfortably inside El Nino territory and rising. So the mechanism is identified, the forcing is confirmed, and the fingerprint is on the storm. Which brings the thread back to where it belongs. The question this video asks is what is wrong in the Pacific, and the honest answer is that nothing is broken in the sense of malfunctioning. The system is operating exactly as the physics says it should. What has changed is where the system is operating, and the reason Dolphin's landfall was unprecedented is that the storm nursery has moved far enough east to put a coastline in range that had never been in range before. But a shifted nursery only explains where Dolphin was born. It does not explain how it survived 13 days at sea, and for that you have to stop looking at the surface of the ocean entirely and start looking underneath it. Part 9. 8 degrees down. Everything we have discussed so far concerns the top of the ocean. Sea surface temperature is what satellites measure, what forecast graphics display, and what almost every discussion of hurricanes and typhoons is built around. It is also the least important number in this story. Roughly 200 meters beneath the equatorial Pacific, a pulse of warm water has been traveling east. It is called a downwelling Kelvin wave, and it is one of the strangest and most consequential features in physical oceanography. Subsurface temperature anomalies within it have been measured at up to 8 degrees Celsius above normal, between depths of roughly 50 and 250 meters. 8 degrees. Not at the surface where you would see it in a satellite image, but down in the dark, in a layer of ocean that most people never think about and no camera will ever show you. Before going further, it is worth knowing how anybody knows that. You cannot see 200 meters down from a satellite. The number comes from the Argo Array, a global fleet of several thousand autonomous floats drifting in the world's oceans. Each one sinks to a set depth, drifts for days, then descends further, and finally rises to the surface while recording temperature and salinity the whole way up, At the surface, it transmits its profile by satellite and sinks again. It is the closest thing humanity has to a continuous body scan of the ocean interior, and it is the reason we can talk about what the Pacific looks like at 200 meters with any confidence at all. A Kelvin wave in this context is not a wave in the sense of something you would see breaking on a beach. It is an internal wave, a deformation of the boundary between the warm upper ocean and the cold deep ocean, and it propagates eastward along the equator over a period of weeks to months. When westerly wind bursts occur over the western Pacific, they push surface water east and depress that boundary layer, and that depression then travels across the entire ocean like a slow-motion ripple in a 200-meter deep layer of water. Where it passes, the warm layer gets thicker. The boundary it is deforming has a name, the thermocline. Picture the ocean as a glass holding two liquids that refuse to mix, warm and light on top, cold and dense below, with a sharp transition between them. That transition is the thermocline, and in the tropical Pacific it is unusually abrupt. You can descend through 100 meters of bath water, and then, within a few tens of meters, find yourself in water only a few degrees above freezing. A downwelling Kelvin wave pushes that boundary deeper as it passes, which means the bathwater layer gets thicker for weeks at a time in whatever part of the ocean the wave happens to be crossing. These waves are slow by the standards of anything else that crosses an ocean. They move at a couple of meters per second, which sounds respectable until you work out that it takes them 2 to 3 months to travel from the western Pacific to the coast of South America. That transit time is one of the reasons El Niño is forecastable at all. When forecasters see a Kelvin wave launch in the west, they know something is arriving in the east on a schedule, and they can say so months in advance. And the thickness of the warm layer, not its temperature, is what decides whether a typhoon lives or dies. We touched on this back when we were looking at dolphins' rapid intensification, when the question was why the ocean's usual break failed to engage. Here is the deeper version of the same story. A storm mixes the water column underneath it, and whether that mixing hurts the storm depends entirely on what is available to mix. If the warm layer is 30 meters thick, the storm reaches straight through it into cold water within hours and chokes on its own wake. If the warm layer is 250 meters thick, the storm can churn as violently as it likes, and every bit of water it brings up is still warm enough to feed it. That is the difference between a typhoon that peaks and collapses in 3 days and a typhoon that crosses an ocean. And it explains something specific about dolphins' behavior that the National Meteorological Center flagged, and that has been sitting unexplained since the beginning of this video. Frequent fluctuations in intensity. Dolphin weakened and re-strengthened repeatedly across 13 days. Every one of those recoveries required the ocean to hand it back the energy it had just spent. A storm sitting over a shallow warm layer does not get second chances. Dolphin got them over and over again. The origin of the current Kelvin wave is worth tracing because it connects back to storms. In April of 2026, an unusual triplet pattern developed across the Pacific, with 2 cyclones spinning in the South Pacific and Super Typhoon Sinlaku in the Northern Hemisphere at the same time. Configurations like that generate strong westerly wind bursts along the equator, and those bursts are precisely the trigger that launches downwelling Kelvin waves eastward. Follow that loop around, because it is the kind of thing that makes this system hard to predict. Tropical cyclones helped generate the wind bursts. The wind bursts pushed the warm water east. The eastward migration of warm water shifted the genesis zone east and deepened the warm layer along the way. And the shifted, deepened nursery then produced a storm born on the international date line that survived long enough to reach China. The storms helped build the conditions that built the storm. The warm pool itself, the physical object we described a moment ago, is described by the Climate Prediction Center as migrating eastward. That is not a subtle statistical signal buried in a data set. That is the largest body of warm water on Earth changing address. There is a practical consequence of all this that forecasters have been wrestling with for years. Rapid intensification is the hardest thing in tropical meteorology to predict, and a large part of the reason is that the ocean's contribution to it is invisible from above. 2 storms can be sitting over sea surface temperatures that look identical on a satellite map, and one of them will explode while the other stalls, and the difference is 150 meters of water that no camera can see. Forecast models have improved enormously at incorporating subsurface heat, but the observations feeding them are sparse compared to the atmosphere, and the errors that remain tend to fall on the side of under-forecasting how strong a storm can get, and the forcing is not finished. NOAA's guidance places the probability of a very strong so-called Super El Nino peaking between November 2026 and January 2027 at approximately 63%. The word super is not marketing. It refers to events where the oceanic Nino index climbs to 2 degrees Celsius or higher, a threshold that has only been crossed a handful of times in the modern record, and every time it has been crossed, the global consequences have run for a year or more afterward. The May 2026 diagnostic discussion put El Nino probability at 82% for the May through July window and 96% for December through February. The event that produced the conditions behind Dolphin is, as of this recording, still strengthening. So when you ask what is wrong in the Pacific, this is the layer where the answer actually lives. Not in any individual storm, and not in the wind speeds, and not in the satellite images of 5 systems on one map. It lives 200 meters underwater in a slab of anomalously warm water that has been sliding east for months and is deep enough that storms sitting on top of it cannot exhaust it. Dolphin is what that looks like from above. Which raises the obvious next question, and it is the one that turns this from a story about one storm into a story about a basin. If the conditions that produced Dolphin are basin-wide, what else were they producing at the same time? The answer was visible on a single satellite image on the afternoon of August 9th, and it is the reason this video exists. Part 10. 3. At once. Picture the satellite image from the afternoon of August 9th. On the left edge of the frame, a large white spiral is grinding into the Chinese coast, its outer bands already sweeping across Taiwan and the East China Sea. That is Dolphin. Move your eye east and slightly north, out past Japan into the open Pacific, and there is a second spiral, broad and slightly ragged, tracking west toward the Japanese main islands. That is Chanhom. Drop your eye south and east again, down toward the Mariana Islands, and there is a third circulation, small and new. That is Pelu, which had existed for a matter of hours. And further east still, another knot of convection, flagged and numbered but not yet named. 3 named typhoons and an invest, in one basin, in one frame. Chinese state media described it as a rare 3-typhoon situation, which is the sort of phrasing that gets used often enough to lose its impact. So let us take the 3 of them one at a time, because each is doing something worth understanding, and one of them is doing something genuinely odd. Start with Chanhom, because it is the one with a coastline in its immediate future. The Joint Typhoon Warning Center designated it 14W. The Japan Meteorological Agency counted it as typhoon number 15 of the year. On August 9th, it was positioned roughly 1,339 kilometers east-southeast of Misawa in northern Japan, tracking westward at 26 kilometers per hour, which is 14 knots. Its minimum central pressure sat at 991 hectopascals. That pressure figure tells you most of what you need to know. 991 hectopascals is barely below standard sea level pressure. Compare it to Dolphin's 910 at peak, and the difference is stark. Chanhom is not a powerful storm, but look at where it came from. Chanhom tracked northwest out of the vicinity of Wake Island. Wake Island. The same lonely atoll that Dolphin passed within 180 nautical miles of at the moment it hit Category 5, out at the far eastern edge of the basin where the storm nursery is not supposed to reach. 2 of the 3 named typhoons active on August 9th traced their origins back to that same remote stretch of the Pacific, thousands of kilometers east of where the climatology says these systems come from. That is the fingerprint, showing up twice in 1 week on 2 different storms with 2 different outcomes. One of them intensified into a record breaker, the other stayed weak. What they share is a birthplace that should not have been producing either of them. The bulletins tracking Chanhom's approach came in part from American military weather services, and the reason is worth a sentence. Northern Japan hosts substantial United States military infrastructure, and Misawa Air Base and Yokota Air Base both appear in the forecast language for exactly that reason. When a storm's projected landfall gets described as 245 miles south of Misawa and 110 miles north of Yokota, that is a forecast written for people who need to decide whether to move aircraft. The forecast reflected that. It was expected to peak at around 60 miles per hour of sustained wind late on Monday evening, August 10th, and then weaken as it approached Honshu. Landfall was projected for Tuesday evening, August 11th, somewhere between 7 and 11 o'clock at night, roughly 245 miles south of Misawa and 110 miles north of Yokota Air Base. From there, the Joint Typhoon Warning Center expected it to pass through the central portion of northeastern Honshu overnight into Wednesday, crossing into the Sea of Japan as a tropical depression. The Japan Meteorological Agency's own guidance had it approaching Japan's Pacific coast by August 11th before entering the Sea of Japan. The operative description forecasters used was large but weak, and that combination has a very specific meaning for what happens on the ground. A weak storm will not take roofs off. What a large storm does, regardless of its wind speed, is deliver an enormous volume of water over a wide area for an extended period, and the terrain of northeastern Honshu is the worst possible canvas for that. Tohoku is mountainous, its rivers are short and steep, and its valleys funnel water quickly into populated lowlands. A slow, broad, moisture-laden system crossing that landscape produces flooding and landslides out of proportion to its category. The practical guidance for anyone travelling in Tohoku or on Hokkaido between the 11th and 13th of August was to expect delays rather than cancellations, which is an accurate summary of a disruption event rather than a disaster. There is also a timing problem for Japan specifically. Dolphin crossed Okinawa on the 6th and 7th of August. Chanhom was forecast to cross northeastern Honshu on the 11th into the 12th. That is 2 tropical systems making landfall on Japanese territory inside of 6 days, at opposite ends of a country that stretches 3,000 kilometres from end to end. Different prefectures, different hazards, different emergency response networks, but the same national resources, the same airline networks, the same rail operators, and the same national broadcaster running the same warnings back to back. Emergency management scales badly under that kind of load. A single event, however severe, can be met by concentrating resources. 2 events in a week, separated by the full length of a country, means splitting them. But hold Chanhom next to Dolphin for a moment, because the contrast is the point. Dolphin was born on the date line, travelled 6,000 kilometres, and arrived as a Category 1. Chanhom formed much closer to Japan and will arrive as a weakening tropical storm. 2 systems, wildly different histories, converging on the same week in the same region. That is what a crowded basin looks like from the perspective of the people underneath it. Not one big threat, but a queue. Now the 4th object in that satellite frame. On August 7th, forecasters had flagged a disturbance near the Mariana Islands and given it the designation Invest 98W. Its position was approximately 19.4 degrees north, 146 degrees east. Maximum winds of 20 knots. Minimum central pressure of 1,009 hectopascals. By any operational standard, a nothing, a patch of thunderstorms. The Joint Typhoon Warning Center placed it under a tropical cyclone formation alert, meaning forecasters assessed that development into a tropical cyclone was likely within 24 hours. 2 formation alerts in the same week, in the same stretch of ocean, on 2 separate systems. The other one, remember, was on Kujira's remnants. That is what the environment was doing in early August. It was not just permitting cyclone development. It was actively pushing marginal systems across the threshold, twice, in a basin that already had multiple named storms running. Consider what that means for the people living in the path of it. The Mariana Islands are not empty ocean. Guam, Saipan, Tinian and Rota carry a combined population well into 6 figures, spread across islands that are small enough that a single storm covers all of them at once. When forecasters put a formation alert on a disturbance near the Marianas, they are telling a community that something might be about to grow in their front yard, with hours rather than days of lead time, because a system forming that close does not give you the long approach that a system from further east does. The Mariana Islands sit in the middle of all this, and they have been in the middle of it all season. This is the same island chain that took a direct hit from Super Typhoon Baby in early July, and we will come back to what happened there, because it establishes that the pattern we are looking at now started weeks before Dolphin existed. Which brings the thread back around. Every one of these systems, the one hitting China, the one approaching Japan, the invest near the Marianas, and the one we have not properly looked at yet, is drawing from the same reservoir. The same eastward migrating warm pool, the same deepened warm layer, the same strengthening El Nino. They are not 4 separate stories that happen to be occurring simultaneously. They are 4 outputs of one machine, and the machine is running hot. And the 4th output was doing something that made forecasters look twice. Part 11. The Storm Moving the Wrong Way. At 2 o'clock in the afternoon on Sunday, August 9th, while Dolphin was 3.5 hours from landfall in Zhejiang, a new tropical storm formed in the western North Pacific. It was given the name Peilu, and it became the 16th typhoon of the 2026 season. The name was contributed by Macau and refers to a common migratory bird found in the region, which is a small piece of irony given what the storm proceeded to do. Its position at formation was about 740 kilometres northwest of Saipan, with winds up to 65 kilometres per hour near the centre. Modest, unremarkable, exactly the kind of system that appears in that part of the ocean regularly during peak season. Then the forecast came out. Peilu was expected to move eastward at 25 to 30 kilometres per hour and gradually strengthen. Eastward. I want to make sure the strangeness of that lands, because it is easy to skim past a direction on a forecast bulletin. Tropical cyclones in the northwest Pacific move west. That is not a tendency, it is close to a rule, and the reason is the same subtropical ridge we discussed at the start of this video. Storms forming on the southern flank of that high-pressure system get carried west by the easterly flow around it. That is why typhoons threaten the Philippines, Taiwan, Japan and China, and why nobody in Hawaii spends much time worrying about systems from the far western Pacific. The conveyor runs one way. A storm that forms near the Marianas and then heads east is running against the conveyor. There are legitimate ways this happens. If the subtropical ridge has a weakness in it, a break where a mid-latitude trough has dug down from the north, a storm can slip into that gap and get pulled poleward and then eastward by the westerly winds above it. A system positioned on the northern or eastern side of the ridge rather than the southern flank will be steered by a completely different part of the flow, and in a basin with multiple storms in it, one system's circulation can influence another's track directly. There is a forecasting dimension to this that goes beyond curiosity. A storm moving east is a storm whose track the standard mental model gets wrong. Every piece of institutional intuition in the region, every rule of thumb about which islands to watch and which coastlines to warn, is built on the assumption of westward motion. When a system violates that, the forecast confidence drops, the cone widens, and the set of places that need to pay attention becomes harder to define. It also means that whatever is steering it is not the pattern that normally steers storms in that part of the ocean, which is itself information about the state of the atmosphere. By 8 o'clock that evening, Philippine civil defense authorities were describing Peilu as roughly 2,200 kilometers east of extreme northern Luzon, with winds of 65 kilometers per hour, gusts to 85, moving east-southeastward at 25 kilometers per hour. It was being monitored outside the Philippine area of responsibility by the country's weather agency, with the note that it might enhance the southwest monsoon in the coming days. That last detail is worth pausing on. Here is a storm moving away from the Philippines, in the wrong direction, at a distance of more than 2,000 kilometers, and the national forecasters are still warning about it. Because a tropical cyclone sitting out in the open Pacific pulls the southwest monsoon flow toward it, and a strengthened monsoon flow means more rain over Luzon regardless of where the storm itself goes. Peilu did not need to approach the Philippines to make the Philippines wetter. It just needed to exist and to be strong enough to tug on the pattern. For Luzon, that mattered. The island had already taken Kujira's landfall on the 6th, then absorbed monsoon rain, enhanced by Dolphin as it passed to the north, and was now facing a third round of monsoon enhancement from a storm 2,000 kilometers away that would never come near it. 3 separate systems, none of them individually catastrophic, delivering rain onto ground that never got a chance to drain between them. That is a different kind of hazard from a single major landfall, and it is a hazard that crowded basins specialize in. So how unusual is it actually to have 3 named typhoons in this basin at the same time? Rarer than you would guess. 3 simultaneous typhoons in the Western Pacific occurred on the 8th of July 2015, and that was the earliest calendar occurrence ever recorded, breaking a record that had stood since the 10th of July 1972. Before 2015, the previous instance of 3 at once was the 24th of October 1994. That is the frequency we're talking about. Not annual, not even close. 4 at once is rarer still. It happened in mid-March of 2015, and it happened again in November of 2024, when Yinqing, Toraji, Usagi and Manyi occupied the basin together, marking the first time since records began in 1951 that so many storms coexisted in the Pacific Basin in November. That November 2024 cluster deserves a moment on its own, because November is supposed to be the tail end of the season. Yinqing, Toraji, Usagi and Manyi lined up across the basin in a chain, and several of them tracked toward the Philippines in succession, delivering landfall after landfall onto the same islands within days of each other. The satellite imagery from that stretch, 4 cyclones strung across the western Pacific like beads, is some of the most arresting weather imagery of the decade. And the record it broke reached back to 1951, which is the year the modern observational record for this basin begins. Now notice the years in that list. 2015 appears twice. 2015 was a super El Nino year, one of the strongest events ever recorded, and it produced both the earliest triple typhoon occurrence on record and a 4-storm cluster in March. That is not a coincidence, and it is the same fingerprint we have been tracing all the way through this video. At this point I have to introduce the counterargument, and I want to give it full weight, because it comes from a credible source, and it is correct as far as it goes. Ma Jun, director of the Institute of Public and Environmental Affairs, addressed exactly this question in comments to the Global Times on the 9th of August. His position is that early August is a peak period for typhoon activity, typically seeing the most typhoon formations of the year, and that the occurrence of multiple typhoons during this period, including severe ones, is normal. His mechanism is sound, and it is important. By early August, he explained, the ocean has absorbed and accumulated energy for more than 6 months, while the atmospheric circulation is also favourable for the formation and development of typhoons. That is the seasonal cycle doing exactly what the seasonal cycle does. The Northwest Pacific has been soaking up sunlight since February. The monsoon trough is at its most active. The subtropical ridge is positioned where it produces the most genesis. If you were going to pick one week in the year to find several typhoons in this basin at the same time, you would pick this one. So here is how I would hold both of those things at once, and I think it is the most honest reading available. The number of storms is normal. Ma Jun is right about that, and anybody presenting the count of 3 or 4 systems on a satellite image as evidence of a broken planet is overreaching. Early August in the Northwest Pacific is a busy place and always has been. The geography of the storms is not normal. That is what China's National Meteorological Center said, in its own bulletins, about its own coastline. A typhoon forming near the international dateline and going on to strike China at tropical storm intensity or above has never been recorded before. That statement is not about how many storms there were, it is about where one of them started. Those two claims do not contradict each other. The count is seasonal, the coordinate is not, and the coordinate is the one that has no precedent in the file. Which leaves one thing left to check before we can talk about what happens next, and that is whether the record book really is as empty as it appears, or whether we are simply looking at a very short record. Part 12. The year. The record was set. Before Dolphin, this season had already put a storm somewhere it had never been. On the night of the 5th of July, 2026, Super Typhoon Baby passed over the United States Northern Mariana Islands and Guam at peak intensity, carrying winds of 290 kilometres per hour. That is 180 miles per hour. The eye of the storm went directly over Rota, the smallest and least populated of the 3 main Mariana Islands, with sustained winds around 180 miles per hour, making Bavi the strongest storm ever recorded to hit that island. The damage across Guam, Rota and Saipan was extensive. Power poles and lines came down, roads flooded and filled with debris, buildings were damaged including a water distribution station on Rota, which is the sort of loss that turns a wind event into a public health problem. Nearly 100 FEMA officials deployed to Guam to work the response, and nobody died. Not on Guam, not in the Northern Marianas. A storm at the absolute ceiling of the intensity scale went directly over an inhabited American territory, and the death toll was 0, which is a remarkable statement about building codes, warning systems, and a population that has been through this before. Rota is worth dwelling on for a second because of what it says about scale. It is the smallest of the 3 main islands in the Commonwealth of the Northern Mariana Islands, a place of a few thousand people, close enough to Guam that the two share a weather forecast, and far enough that they do not share infrastructure. When a storm's eye passes directly over an island that size, there is no unaffected side of it. There is no interior to retreat to, and no neighbouring district to send help from. The entire community is inside the eye wall at the same time, and when it passes, everything that keeps the place running, including the station that distributes its water, has been inside it too. Bavi was the 3rd Category 5 tropical cyclone of 2026. Dolphin, at the end of the month, was the 5th. All 5 had occurred in the Pacific. 5 before the end of July. The all-time record for Category 5 storms globally in a single calendar year is 12, and that record belongs to 1997, which is where this story has to go next, because 1997 is the only year in the observational record that offers a genuine comparison, and it offers more than one. 1997 was a super El Niño, not a moderate event, not a borderline one, but one of the strongest ever measured, and its effects propagated through the global climate system for well over a year. In the Northwest Pacific, it produced a season that has never been matched. According to the Joint Typhoon Warning Center's assessment, 11 tropical cyclones attained super typhoon status that year, 10 of which reached Category 5. 10 Category 5 typhoons in a single basin in a single season remains the highest count on record. Sit with that number for a moment, because it is easy to let it slide past. 10 Category 5 typhoons. 10 storms in one season, in one ocean, each of them at the absolute ceiling of the intensity scale, each of them capable of erasing a small island. Most years a basin produces 1 or 2. Some years it produces none. 1997 produced 10, and it did so because the ocean underneath them had been rearranged by the strongest El Niño anyone had ever measured at that point. Their names are worth listing, because seeing 11 of them in a row does something that a number cannot. Isa, Nestor, Rosie, Winnie, Bing, Oliwa, Ginger, Evan, Joan, Keith, and Paka. That last one is the reason we are here. Paka's genesis occurred in the Central Pacific Ocean in late November, 1997, near the end of the official Central Pacific hurricane season. The tropical depression that became Paka formed on the 28th of November, and the Central Pacific Hurricane Center declared it a tropical storm at noon, Coordinated Universal Time, on the 2nd of December. The mechanism that created it is one we have already met in this video. A strong equatorial westerly wind burst developed southwest of Hawaii, and out of it came twin tropical cyclones, one on each side of the equator. Paka spun up north of the line. Cyclone Pam spun up south of it. Westerly wind bursts of that kind are exactly what launches downwelling Kelvin waves eastward, and they occur when El Niño has already weakened the trade winds enough for the westerlies to break through. On the 7th of December, at 6 in the evening Coordinated Universal Time, Tropical Storm Paka crossed the international date line and entered the tropical northwestern Pacific. It went on to become one of the 11 super typhoons of that season, the last tropical cyclone of both the 1997 Pacific hurricane season and the 1997 Pacific typhoon season, and it eventually delivered a devastating blow to Guam. So we have a precedent. Sort of. Here is where the comparison holds. Both storms are products of the same forcing, both formed at the far eastern boundary of the basin, or beyond it, during a strong El Niño, in association with an anomalously eastward displaced convective environment. Both went on to become extremely intense. Both are, in their own ways, evidence that when the warm pool moves east, the storm nursery moves with it. Here is where the comparison breaks, and the difference is the whole point of this video. Peka formed east of the date line and crossed into the Northwest Pacific as an already existing system. Dolphin formed on the date line within the basin at 176.9 degrees east and never crossed anything. Paka's ultimate target was Guam, roughly 3,000 kilometers from where it entered the basin. Dolphin's ultimate target was the coast of mainland China, more than 6,000 kilometers from where it was born, on the far side of the Philippine Sea, the Ryukyu Islands, and the East China Sea. 1997, the strongest analogue the record can offer, from the most extreme El Niño of the 20th century, produced a storm that made it part way. 2026 produced one that made it all the way. And 2015, the other super El Niño in recent memory, produced the earliest occurrence of 3 simultaneous typhoons ever recorded in this basin, on the 8th of July, breaking a record that had stood since 1972. That is the same year that also produced a 4-cyclone cluster in March. It is worth remembering what a super El Niño does beyond the storm counts, because it puts the current forecast in perspective. The 1997-98 event reorganized weather patterns across most of the planet for well over a year. It shifted rainfall across the tropics on a continental scale, drove drought in some regions and flooding in others, altered fisheries in the eastern Pacific, and left a signature in the global temperature record that was visible for years afterward. These events are not regional curiosities. They are the largest single source of year-to-year variability in the entire climate system. Line those 3 years up: 1997, 2015, 2026. In each case, a powerful El Niño, In each case, an eastward displaced storm nursery, and in each case records broken in the specific category of where and how many rather than simply how strong. The pattern is consistent, which is reassuring in one sense, because it means we are looking at a known mode of variability rather than something inexplicable. It is less reassuring in another sense, which is that each successive iteration of the pattern has produced a storm that travelled further from the nursery than the last one did, which brings us to the objections, because a claim like the one at the centre of this video, a first on record, invites some very reasonable pushback, and it deserves an honest hearing. Part 13. What the record cannot see. The strongest argument against everything I have told you so far is that the record book is young. It is a good argument, and I want to make it properly before I answer it, because the version of this that gets dismissed with a wave of the hand is not the version worth engaging with. Here it is. The modern observational record for tropical cyclones in the Northwest Pacific begins around 1951. Reliable, continuous, global satellite coverage of tropical cyclones arrives later than that, building through the 1960s and 70s, and only becoming genuinely comprehensive in the decades after. Before that, we knew about the storms that hit populated coastlines, the storms that ships ran into, and the storms that military aircraft happened to fly through. A typhoon that formed on the international dateline in 1890, spun through the middle of an empty ocean and dissipated near Taiwan would have left almost no trace in any record anywhere. It is worth understanding what tropical cyclone observation actually looked like before satellites, because it explains where the gaps are. For most of the first half of the 20th century, a storm in the open ocean was known only if something ran into it. Ship logs were the primary data set, which means the record traces shipping lanes rather than storms. Aircraft reconnaissance, flying instrumented planes directly into cyclones to measure them, began in the 1940s and improved things dramatically, but it too could only fly where somebody had a reason to send it. The eastern half of the Northwest Pacific, empty of both shipping lanes and strategic interest, was among the least observed patches of ocean on Earth. So when China's National Meteorological Center says this has never happened since meteorological records began, the honest translation of that phrase is this has never happened in the period during which we would reliably have noticed. Those are different claims, and anyone telling you otherwise is overselling. I want to be clear that I think this objection is correct. The qualifier is real, it matters, and it should be stated every time a first-on-record claim gets made about anything. Now here is why it does not dissolve the finding. The satellite record is short, but it is not short in a random way. It covers the period from roughly the 1970s to the present, and that period happens to include the three strongest El Niño events of the modern era: 1982 to 83, 1997 to 98, and 2015 to 16. Those are precisely the years in which the eastward genesis shift would have been most extreme, and therefore precisely the years most likely to have produced a dolphin analogue. They were all fully observed, with satellites overhead the entire time. And what did those years produce? The strongest of them produced Paka, which formed east of the dateline, crossed into the basin, and hit Guam. Which is close, and which is exactly the point. The record is not blind in the places where an analogue should be hiding. We looked in the most likely years, with good instruments, and the closest thing we found stopped 3,000 kilometres short. That does not prove no such storm ever existed before 1951. Nothing could prove that. What it does establish is that under the conditions most favourable to producing one, across the entire era in which we would have caught one, we did not catch one until now. There is a second category of objection, and it arrived, as it always does, within hours of the satellite loops going viral. Claims circulating online during major typhoon events routinely assert that storm tracks are being manipulated. Sometimes the accusation involves weather modification programs, sometimes ionospheric heating facilities, sometimes unnamed state actors with unspecified capabilities. Dolphin's unusual origin point and its long, straight westward track toward a specific country attracted exactly this framing, and I understand why. A storm that comes from a place storms do not come from, and then travels 6,000 kilometres to a populated coastline, has a narrative shape that invites the question of whether somebody aimed it. The answer is quantitative, and it is not close. A mature tropical cyclone releases energy at a rate that dwarfs human industrial capacity by orders of magnitude. Depending on which energy accounting you use, the latent heat release inside a large typhoon runs to hundreds of times humanity's entire electrical generating capacity, continuously, for days. There is no facility, no program, and no plausible technology that adds or subtracts a meaningful fraction of that. Cloud seeding, the only weather modification technique deployed at any scale anywhere, works by introducing particles that give water vapor something to condense onto in a cloud that was already going to produce precipitation, under conditions that were already marginal. Its effect sizes are debated even by its practitioners. It cannot create a tropical cyclone, it cannot steer one, and it cannot intensify one. But the decisive argument is not about energy budgets at all. It is about the track. Dolphin's path was not mysterious. It followed the southern flank of the subtropical ridge, which is the standard steering mechanism for nearly every typhoon this basin has ever produced, and its westward bend occurred where the geometry of that ridge dictated it should. If you had shown a forecaster the position of the ridge and the storm's location without telling them anything else, they would have drawn approximately that path. There is nothing in Dolphin's track that requires explanation. The anomaly in this storm is where it started, not where it went. And the mechanism that explains where it started is a warm pool migration that has been measured, mapped, and published in the scientific literature for decades. Then there is the third objection, which is the darkest one and the easiest to answer, the claim that authorities knew and did not warn people. The timeline says otherwise, in unusual detail. Fishing fleets sheltered on the 5th of August, 4 days ahead. Provincial and national emergency responses activated on the 6th, 3 days ahead, while the storm was still 1,100 kilometres offshore. Ferry routes suspended, coastal attractions closed, and shipping lanes controlled the same day. A red alert on the 9th. More than 1 million people evacuated and more than 1,000 flights cancelled before landfall. Whatever else this event was, it was not a warning failure. It was arguably one of the more aggressive pre-landfall mobilizations of the year, and the fourth objection is the one I have the most sympathy for, because it is a criticism of coverage rather than a conspiracy theory. The complaint that El Niño has become a catch-all excuse, invoked to explain any weather event that needs explaining. That criticism is fair, and the way to avoid deserving it is to be precise about which claims the science supports. The eastward shift of tropical cyclone genesis under El Niño conditions is supported. It has a documented statistical signature, the movement from a distribution concentrated west of 160 degrees east toward one extending to roughly 170 degrees east. It has a physical mechanism that can be traced step by step from trade wind weakening through warm water displacement to convective migration. It has been reproduced across multiple independent studies. The claim that El Niño caused Typhoon Dolphin is not supported, and I am not making it. Individual storms are not caused by climate modes. What climate modes do is change the odds, and change the geography, and what the evidence shows is that the geography changed and dolphin formed inside the changed geography. Hold those two statements apart and you have an honest account of what happened. Collapse them together and you have exactly the sloppy attribution the critics are complaining about. So the record is short but not blind. The storm was not steered, the warnings were not withheld, and the mechanism is real but does not license single storm attribution, all of which leaves one question standing, and it is the only one that actually matters going forward. Part 14. The part that has not happened yet. Everything in this video so far has been about a storm that is already over. Dolphin came ashore, weakened, and began the slow process of falling apart over the Chinese interior. By the time you watch this, its winds will be a memory, and its rain will be somebody's flood. The record it set is in the books. The mechanism that produced it is not over. That is the sentence I want to leave you with, and I want to build it out of specifics rather than atmosphere, because there are 4 concrete things still unresolved as this video goes out, and each of them is checkable. The first is Chanhom. It was forecast to make landfall on northeastern Honshu on the evening of Tuesday, August 11th, sometime between 7 and 11 o'clock, and to cross into the Sea of Japan as a tropical depression overnight into Wednesday. The open question is whether it holds together as forecast and whether its rainfall over Tohoku and Hokkaido stays in the disruption range rather than the damage range. Large but weak storms over mountainous terrain are the category that most often surprises people, because the headline number, the wind speed, is the number that matters least. There is a second dimension to Chanhom that will not be visible in the landfall coverage. Northern Japan spent the summer of 2026 the way most of the Northern Hemisphere did, which is to say hot. ground that has been baked hard sheds water rather than absorbing it, and the first heavy rain onto a dry, compacted catchment runs off faster than the same rain onto ground that has been damp for weeks. The rainfall total that a Tohoku river basin can tolerate is not a fixed number. It depends on what the ground was doing beforehand, and that is the sort of variable that does not appear in a forecast cone. The second is Peilu, a storm forecast to move eastward at 25 to 30 kilometres per hour, while gradually strengthening as a storm behaving unusually, and where it ends up is a direct test of the atmosphere it is embedded in. If it recurves and dissipates harmlessly out in the open Pacific, this was a quirk. If it holds that eastward heading and keeps intensifying, that is information about a steering pattern that has stopped doing what steering patterns in that part of the ocean normally do. It also matters for the Philippines in a way that has nothing to do with Peilu's track. A named system sitting out in the open Pacific keeps pulling on the southwest monsoon, and Luzon has already taken Kujira's landfall, then monsoon rain enhanced by Dolphin, and is now looking at a third round from a storm that will never come near it. Saturated ground has no memory of which storm delivered which centimetre. It only knows the total, and the total is what fails hillsides. The third is Dolphin's own water. The forecast called for the remnants to slow over central and southwestern China, and then interact with cold air, generating further downpours across North China, Inner Mongolia, and southern northeast China from Wednesday the 12th through Friday. The wind phase of a typhoon is over in hours. The water phase runs for a week and gets counted afterward, and the final accounting of what Dolphin did to Chinese river basins will not exist for days after the cameras have gone. And the fourth is the one that dwarfs the other three. NOAA places the probability of a very strong El Niño peaking between November 2026 and January 2027 at approximately 63%. The probability of El Niño conditions persisting through the Northern Hemisphere winter at all is above 96%. The downwelling Kelvin wave is still propagating east. The subsurface anomalies are still sitting at up to 8 degrees above normal, between 50 and 250 metres. The warm pool is still migrating. Every single mechanism that produced Typhoon Dolphin is still being loaded, and it is being loaded harder. Now stack that against the calendar. 16 named storms had formed in the Northwest Pacific by the 9th of August. The seasonal forecast issued in early July called for 28 tropical storms, 19 typhoons and 12 intense typhoons, roughly 40% above the long-term average, and the peak months of the Northwest Pacific season, the stretch that reliably produces the strongest systems of the year, are August, September and October. We are at the beginning of that stretch, not the end of it, and there is a version of this that is worth stating plainly, without any drama attached to it, because it is the version that actually affects people. The consequence of an eastward shifted storm nursery is not that storms get stronger, although the research says they tend to. The consequence is that the set of coastlines within reach expands. A basin whose storms are born at 130 degrees east threatens a certain list of places, and everyone on that list knows they are on it and has built accordingly. A basin whose storms are born at 177 degrees east threatens the same list, plus everything those storms can now reach because they have an extra week of ocean to work with, and plus whatever coastline sits at the far end of a track nobody had drawn before. Preparedness is built on lists, building codes, evacuation plans, insurance models, port infrastructure, the intuition of the people who live there. All of it encodes an assumption about which storms can arrive and from where. When the geography of Genesis changes, those assumptions do not update automatically. They update after something arrives that was not supposed to be able to. Zhejiang was ready this time. Zhejiang is always ready, because Zhejiang has been on the list for as long as there have been lists. The question the rest of this El Niño poses is, who else has just been added to it and does not know yet? I keep coming back to how quiet this record is. There was no image of Dolphin at landfall that looked different from any other typhoon at landfall. There was no wind speed that made anybody gasp. A Category 1 equivalent hit a coastline that absorbs Category 1 equivalents routinely, and a competent country moved 1 million people and got on with it. If you had watched only the footage from Yuhuan or Wenzhou or Shanghai, you would have seen a bad day and nothing more. The record is not in the footage. It is in a pair of numbers that nobody films. 13.2 degrees north, 176.9 degrees east, a coordinate in the middle of an empty ocean, on the international date line, where a storm that would go on to reach mainland China had never previously been born. That coordinate is a measurement of how far the Pacific storm nursery has moved. and the thing about a measurement is that it can be taken again, which is the question I cannot stop turning over, and the one I would like you to hold with me until we know the answer. The eastern edge of the nursery was supposed to be around 170 degrees east. This year it produced a storm at 176.9, and that storm reached a continent. If this El Nino peaks in the window Noah expects, at the intensity Noah thinks is most likely, during the months this basin does its most violent work, then somewhere out past the date line there is a stretch of ocean that has never made a typhoon before. What happens the first time it does